Just that number one.
Okay?
Just run all the way through them.
Yeah. A tangent squared?
Yeah, tangent squared x, yeah.
Okay. What's the first thing you notice about this? There's a trig identity that relates tangent squared to secant squared. It's tan squared plus 1 equals secant squared. So knowing that that trig identity exists, what's the first thing we should do here?
Make the secant squared x.
Yeah, distribute that.
Yeah.
Because we know that we're going to immediately get a secant squared, and that's what we want to do. In other words, we certainly wouldn't want to change everything to sine and cosine. Now clearly, secant times cosine must be 1. Right?
Yeah.
In other words, if you see it, you kind of have to stay one step ahead here. But obviously, secant is 1 over cosine. So you get secant squared minus 1. You might have to interpret there. Does that say cosine fourth?
Yeah, cosine fourth t minus sine fourth t equals 1 minus 2 sine squared t.
That looks like a 3 to me.
Yeah, that's a 2.
It is a 2?
Yeah.
All right, let's see if we can prove it. So, we have everything in sine and cosine. Well, it'd be nice if, in other words, since this is all in sine, how about if we change the left to completely sine?
Okay.
But before we do that, what do we see over here? What is that called?
That's not true identity, is it?
No, it's not, but it's difference of perfect squares. Never forget difference of perfect squares. You need it throughout math. Okay? So what does this factor into?
Cosine squared minus 1.
No.
Or plus 1.
No. In other words, cosine squared minus sine squared times cosine squared plus sine squared.
Oh, yeah.
See why?
Yeah, I got it.
All right. Now we have an identity for cosine squared. So if we replace this with its Pythagorean identity and replace that with its Pythagorean identity, the whole thing is going to be in sine squared. So what is cosine squared? It's Pythagorean identity. You got sine squared plus cosine squared equals 1. So what's cosine squared equal?
2 sine squared minus 1.
Now solve that for cosine squared.
It'd be cosine squared equals 1 minus sine squared.
All right, so that's what we put in place of cosine squared. Minus sine squared. And over here, well, that's the sum of squares, which we can't really do anything with, but we can replace the cosine with 1 minus sine squared plus sine squared. All right, now everything is in sine squared. which means that it's just a question of simplifying the algebra. What does this become?
That'd just be 1 minus sine to the fourth.
No. When you subtract sine squared minus sine squared, you do not get sine to the fourth. You get 2 sine squared. You get 2 sine squared, yeah. In other words, this is no different than an algebra. If I had 1 minus x, that's equal to 1 minus 2x. Okay, so 1 minus sine squared is 1 minus 2 sine squared. And what does this become?
Just 1.
Yeah. So now that answer is 1 minus 2 sine squared. That's what we're supposed to be proving it to be. Okay. Tan x times cotan x. Well, that's 1 right away, right?
Yeah.
Nice to see that. The tan x times cotan x has got to be 1. So what does this become?
1 plus tangent x, or tangent squared x.
Uh-huh. And what's the identity for that?
That's going to be secant squared.
Uh-huh. So secant squared equals secant squared. This is to the fourth. This is the identical one to number 1 or 3, one or the other. Only using the cofunctions. Again, recognize that as difference of perfect squares, because if you can't, it's hard to work with secant to the fourth. In other words, if we're working with squares, then we have 3 different Pythagorean identities we can access. So you have to be able to break that into what?
It'll be secant squared minus tangent, and then tangent squared, and then secant squared plus tangent squared.
And again, each secant squared can be replaced by what?
1 plus tangent squared.
The left thing becomes
hold on, I'm not finished yet.
okay.
It becomes 1 times 2 tangent, 1 plus 2 tangent squared.
Which is what we're trying to prove it to be. Okay, let's look at number 3. This is much like a previous one. Always learn to recognize what that is.
That's 1.
Okay. So this is 1 minus sine squared. Also, definitely recognize what that is. As I said earlier, you're rarely going to come across it in this simplistic format. When they say memorize the identities, they mean memorize the identities plus algebraic manipulations of them. So the most common one you come across is 1 minus sine squared or 1 minus cosine squared. So that's what you want to learn to recognize. All right, 14, oh no, number 13. I guess we're doing these kind of out of order. Is that okay? Or should we do them in order?
No, it's fine.
All right, because these are obviously going to be harder, but in a way it's better that they don't do it. In other words, the way you and I are doing it, it gives you 10 minutes to realize that it's the same problem we had 10 minutes ago. What do you think here? What's a good first step? First of all, we're going to work with the left side, try to make it into the right, which means what? What's tangent x equal to?
Sine over cosine.
Yeah, in terms of all of this stuff over here, it's sine over cosine. So we're going to want to turn it into sine over cosine. How are we going to do that?
Would those two cosines cancel?
No.
Okay.
What we're doing is subtracting fractions. How do we subtract fractions? Finding a common denominator. What is the common denominator going to be?
Sine.
No, it's going to be that.
Yeah.
In other words, a common denominator has to be divisible by both denominators. Cosine wouldn't be, nor would, well, sine would be, but only sine cosine. In other words, the common denominator cannot be less than that, because the best I can do is write that the same way. And then if I try to make this sine cosine, what's the numerator have to be?
Cosine sine, or no, cosine squared.
Always be looking for the 1 minus cosine squared. In other words, they design these problems so that they will work out perfectly. You'll notice that you have not yet found a problem that is not an identity. They do not teach you how to disprove identities. The only thing they teach you is how to prove identities. Okay, what's this become?
1 minus cosine squared x over sine cosine.
Okay, now what's the numerator look like?
Be sine squared.
Simplify.
Go into sine over cosine.
Which is equal to tan. Alright, let's see. Number 4, is that where we're at?
Yeah.
This is actually a more interesting way to do it, because it goes easy, tough, instead of easy, 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 medium, 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 tough, tough, tough. Is that equal to?
1.
1 minus cosine squared. All right, 14. Is that a minus sign? Yeah. Now, worst case scenario with this problem, is we know cotangent x is cosine over sine, and 3 of the 4 terms are cosine or sine, and I can convert secant x into cosine, so we know we're going to be able to solve this. So we kind of want to manipulate the left so that we are going to end up with cosine over sine. So what's the first thing we can do?
Get a common denominator.
Yeah, it would be a mistake to turn that into tangent, I think. That would not be the most efficient way to go. Even though there's a quotient identity that says that's tangent, it's not headed in the direction of cotangent. Maybe, at least I think. But, all right, let's find a common denominator. Let's start right there. What's our common denominator?
Sine, cosine.
What's the left?
Secant, cosine.
What's the right?
Sine, cosine, then sine squared x.
So, we see this a lot. What's this?
Which one?
One on the left circle.
Oh, that is that'd just be 1.
Right. That's what we see a lot of. Okay? Now notice what the numerator is going to turn into.
1 minus sine squared over sine cosine.
Which is what? What's the whole numerator turn into?
Cosine squared.
Cosine squared. And we can take out that cosine and that exponent, and we end up with cosine over sine, which is cotangent. In fact, do you want to go straight to 15 or 16, or you want to just go like we're doing?
Let's actually just go down the right column and do all the hard ones.
Yeah, that's what I was thinking, since I think you get it enough that we can skip to the... These are probably more medium than they are hard. So what are we going to do here? What do we know? What do we know is equal to 1?
Sine over sine, cosine over sine.
What
no,
Pythagorean identity do we know is equal to
1? Sine squared plus cosine squared.
So obviously that's going to be what that needs to turn into, is sine squared plus cosine squared.
Yeah.
Well, what's this?
1.
Sine times cosecant is 1. Sine divided by cosecant, remember cosecant is 1 over sine, and we're looking to turn this into sine squared.
Yeah, so that would be sine squared.
Yeah, and this is going to be cosine squared. So a lot of the secret to verifying trig identities is kind of looking ahead to what you need. In other words, the first time I see this, I know this got to be sine squared plus cosine squared at some point. And surely, clearly, that is sine squared, and that's cosine squared. All right, 1 over secant squared plus 1 over cosecant squared equals 1.
So we're going to have to get this into sine squared plus cosine squared again.
right. What's that?
Cosine.
Squared.
Oh, yeah.
What's that?
Sine squared.
Okay. In other words, don't make these harder than they are. Some of them are very, very straightforward. All right. Now, this looks like it could be relatively difficult. But remember, when we see that, we're thinking multiply by what? Immediately?
Sine.
By the conjugate. Where's the equal sign here? Is it right here?
Yeah.
Well, let me think for a second. Cosecant is 1 over sine. Cotangent is cosine over sine, so that becomes cosine over sine squared. So, let's go ahead and do the obvious first step. First of all, what's the more complicated side?
Say the right side.
And that's actually the left. And the reason is that the left is division by a binomial term, whereas the right is just subtraction from one term minus another term. So let's definitely work with the left. And there's really only one thing you can do with that, which is what?
The conjugate.
Yeah. The reason is it's going to allow us to turn the bottom into 1 minus cosine squared, which is sine squared. And that's a key thing, to be able to turn two terms, especially these two terms, into one term. So the top becomes 1 minus cosine x. The bottom becomes what?
1 minus cosine x squared.
Which is?
Sine squared.
All right, so that's where we start. And over here, well, I can see, what is that equal to? That's 1 over sine squared, right?
Mm-hmm.
Well, since we got a sine squared in the denominator, that is going to be 1 over sine squared. We're getting closer. And then if we just use the quotient identity for cotangent and the reciprocal for cosecant, what does the top become? In other words, it's 1 over sine. That's the cosecant. Cotangent is cosine over sine. See where we're going with this?
Yeah.
Well,
So then that turns into minus cosine over sine squared?
Yeah, turns into the same thing. Now, did I violate anything by manipulating both sides of this thing? I don't think so. I don't think your teacher would take off any points at all for that.
Okay.
Not usually the way I do it. I usually try to turn the left directly into the right, but sometimes it's easier to do that. And it doesn't matter. In other words, it's just as sound, even if you manipulate the right side. At least I think. I would be very surprised if your teacher objected to that. Well, this looks familiar. if you'll notice, this is the same thing we just had, only with the cofunctions. And with a negative sign here and a positive sign there. But it doesn't matter. 1 minus sign doesn't turn into much that resembles this over here. I mean, I suppose I could turn sine into 1 over cosecant, but I don't see any cosecants over there, so that's not going to help. So let's do the same thing. Multiply by the conjugate. Because the one thing we know for sure is when we multiply by the conjugate, the bottom turns into 1 minus sine squared, which can be replaced with cosine squared. So we end up with 1 plus sine in the numerator and cosine squared in the denominator. And again, I can see that that's 1 over cosine squared, and that's going to be something over cosine squared, sine over cosine squared. So that becomes 1 over cosine squared plus 1 over cosine times sine over cosine. That's the same as that. Now let's try to do one more. Aha, secant x minus 1. Now that's a completely different story. Before I see anything else on this problem, I know that if I multiply that by the conjugate, I get this, but that's nothing. What is that? Oh, that is something. That is tangent.
Yeah, that's tangent.
Yeah, that is tangent squared. Okay, excuse me. And that's the minus sign there?
Yeah.
Well, that's very useful to know. If I can somehow turn that into tangent squared, I already have a tangent squared in that denominator, so I'll be able to manipulate them. And we know cotangent squared is 1 over tangent squared. So multiplying this by the conjugate seems to be the perfect way to go. So what's the new numerator and denominator?
Secant squared x minus 1, and then the numerator will be cosine.
Hold on. Remember, I'm multiplying this left side by the conjugate, which means secant plus 1 over secant plus 1. I can only multiply something by the number 1. So that gives me cosine x times secant plus 1 in the numerator. The denominator becomes secant squared x plus 1, which I can replace with tangent squared x. I already have that there, so that's perfect. Cosine over tangent squared x. And let's just make that read 1 over tangent squared x. That means this whole thing must be 1. What's cosine? What's cosine times secant?
Cosine squared.
Cosine times secant. What's secant? It's 1 over cosine?
1 over cosine.
So cosine times secant is 1.
Yeah.
So this becomes 1 plus cosine minus cosine. That becomes 1. Our denominator is already tangent squared. All right. Now, I don't have any more words of wisdom on verifying trig identities. It's, as I said in the previous couple sessions, it's kind of an art. Just practice makes you better, and that's all I can say. Practice makes you better, and it requires 2 skills. You have to know your 11 basic trig identities really well, and you have to use this system of multiplying by the conjugate when it applies, and adding or subtracting fractions when it's appropriate. Those are the three things you need to do to be good at verifying trig identities. Number one is knowing your identities. But that's not it. It's more than that, as we've seen. You got to be able to know when to multiply by the conjugate and when not, and stuff like that.
Okay.
All right. Let's see. You have a session tomorrow at 8:30. I will talk to you then.
All right. Thank you.